In this video, we're going to introduce numerical optimization, and in particular, we're going to use the context of the projects. So many design problems and applications involve the search for the best possible parameters to achieve a goal. And we can think of several examples, such as for the truss project, finding the joint locations, specifically the XY locations, that lead to the maximum supportable load. If we think of all possible designs, there's going to be a load that breaks each of those designs if it's applied to the same location. As we tweak the locations of the joints, that's going to vary, and one design is going to give us the strongest maximum supportable load. We can also think about the heat question, the cooling fin problem. There, what we can imagine is that the depth, width, and possibly the locations of the cuts are going to affect the properties of the cooling fin, and then we might want to achieve some kind of minimization goal, and something like minimizing the internal temperature of the fin. Last but not least, if we're looking at the roller coaster, then what we could move there are the XY locations of the supports. And if we do that, we might be able to achieve some goal, like reach the end of the track in the minimum time, in the shortest time. So notice that these are fairly complicated relationships. The XY locations of a truss define the truss, but then there's a number of calculations that have to happen before we can compute how much of a load a certain design can support. But we'd like to search over the space of possible locations. In other words, move the joints around to achieve the maximum supportable load. These are things we'd like to automate as much as possible, because we think the computer can probably test different locations and varieties of locations faster than we might be able to by hand. In terms of the structure of the problem, one key ingredient for our purposes is that there's going to be a single variable of interest, which means there's a single scalar output value. In the case of the truss, it's the maximum external load. That's one number. In case of the cooling fin, it's the temperature. In case of the launch off the end of a roller coaster, it might be the distance traveled. But we can compare designs by the one number that describes them in terms of the output. With that in mind, we can then focus on the parameters or the inputs that affect this value. So basically the same list we just talked about: the XY, the joint locations, the cut depth, width and location, and for the roller coaster, the XY of the supports for the track. So this is a single variable output, but this is multiple parameters. In fact, one XY for every joint, but certainly not a small number of inputs, and that's true for all three of these scenarios. We want to be able to play with, experiment with, try out up to 10, 20, maybe 30 values and see which one leads to the single best value for the output. A bit of terminology. The function that transforms our input, that 2, 3, 5, 10, 30 inputs, into the output that we care about, is called an objective function. And this, in fact, is going to be simpler than some of the other work we've seen recently. It's literally going to be a function that takes in a vector of values and spits out some new quantity, some single quantity. Our goal is going to be to experiment with the x values to either maximize or minimize the output of this function. Now, this is not completely new territory for us. When we've looked at optimization before, say in APS-C courses, we looked at optimization with the multivariate calculus as being a point where the gradient of the function equals the zero vector. remember this construction. And this is the multivariate version of the set f prime equal to 0 formulation. And this is something, again, if we can do analytic optimization, we should definitely do that. If we can get a nice function, a formula that we can differentiate, set the derivative or derivatives equal to 0 and solve, go to town, do that for sure. However, in most interesting applications, we don't have a formula, or we can't compute its derivative, or any number of obstacles come up in this setup and solving procedure. So this is a great concept. It works when the applications are relatively simple, but thinking back to these kinds of examples, XY joints, cut locations, there is no simple formula that's going to tie those to the output value that we care about. And so finding a derivative doesn't really have any meaning there. So what do we do instead? We go to numeric optimization. Again, we think of numerical methods as something we have to resort to. Because it's not our first choice, we should do the analytical methods if they are available to us. If we do resort to them though, here's what we're getting ourselves into. The most apt metaphor is blind hill climbing. This is where you imagine yourself literally on a surface and someone has blindfolded you. You know maybe what height you're at now, and let's say you're on a map. You know where you are right now, and you can figure out what height you're at, but you don't know what the rest of the surface around you looks like. So the best you can do is maybe take a step and go up or down. Where did I end up? And based on that response, either keep going in that direction if you were going up and trying to maximize, or if that step took you up, then you might want to go the other direction, or maybe take a 90-degree turn. The idea is we have to visit points point by point when we're doing this in MATLAB or any programming language, because that's how computers work. They can just evaluate a function at specific locations and then compare their properties, and hopefully, with some mathematical insight, find a strategy that takes us towards a max or a min. More formally, the algorithm says we're going to have a starting point, xi, and it's a vector, so it can be, say, 30 different numbers in one of our more complicated scenarios. We're going to then pick 30 new numbers, tweak all the values just by a little bit. That's our step in this operation here. Find the height using our calculation function there, and hope that we went uphill, or that we improved our function value. In the end, we're going to generate a sequence of locations. So thinking about walking around sort of in a jump-like fashion, chess moves, and we're going to know the function values at all of those locations. And the difference between various algorithms is going to be mainly about how quickly they can find their way to a peak or a valley, whether they find a global max instead of local maxes as they get searching, and how well they work on a variety of different problems, because you can already feel there might be differences between the heat, the roller coaster, and the truss problems. In this course, we're going to look at two different models in MATLAB, two different functions that do this, and do some informal comparison about these techniques. Now, there's an important note before we go much further, which is how we describe optimization. Usually, when we're getting into these kinds of problems, we think of optimization mostly as maximization. That's our first instinct, to make things larger, stronger, more profitable. However, there are good historic reasons from the physics community where they were looking for low energy configurations, and that's where a lot of these algorithms came from, where it just became a habit to look for minima in functions. I think if I want to minimize a function, that's great if there's a routine that does that. But what if I do want to maximize? If we want to find a local max of some formula, how does that help me having a minimization tool? Well, the nice thing is, if we want a max, and think of this as some kind of function here, there's a point at the top of there, critical point at the top, we're doing our blind hill climbing. I'd like to be able to work my way up to the top there, if that's my function of x. Well, a minimization routine is not going to head towards the top, it's going to head down towards the bottom. However, if we graph -1 times f of x, what that does is takes all the peaks and turns them into valleys. We'd have the same basic shape, just flipped upside down. And if we look for a minima of that function, we're going to find a location, and that location is going to be exactly the same xy position, or x vector position. The same x is the min for negative f of x and the original positive f of x. So if we have a minimization routine, but we want to maximize, we just take the function that we have that we want to maximize, multiply it by -1, and then let that be our function for the optimizer. That makes a lot more sense in the context of a problem. We have some practice problems with that conversion required that'll introduce you to that. So that's the main background for optimization tools. We're going to get into the mechanics through an example next.